All right, so we minimize the error, minimize that E in the equation. We're minimizing the distance of all of the points to the line. And we get some sort of, not only do we minimize, we can also get a value that tells us the goodness of fit of our model to the data. And I can give you two examples here. AA as a function of BB, CC as a function of BB. And what I can see here are two models that are fit, and you can already tell that the distance of those points to the model is actually a lot smaller in the top figure than it is in the smaller figure. So this one has a better fit. Okay, so it will have a higher indicator of goodness of fit. So there are two reasons for error. One is the regression sum of squares. So here's my line of best fit, and I have some sort of distance from that line, which is to do with the noise in my data, or because there's another factor that I'm not taking into account. Okay, so my model is not perfectly describing the relationship between y and x. There are many reasons for that. Okay, so I have the line of best fit. This is the best I can do. And then I have the sum of squares. So those distances squared, if I just take these distances and add them up all together, I'm going to get 0. So I square them before I add them up. And the bigger they are, the bigger those distances, the worse this line of best fit describes the data, right? But we have a regression sum of squares. We also have the total sum of squares, which is to do with, here is the mean of y, and this is how much these points deviate from the mean. Okay, so if I, which is why I actually have a slope here, I have deviations from the mean that are growing as x deviates from the mean as well. So as I get further from mean x, I have a higher total sum of squares. So these distances between this point and the mean are to do with two things. One is the effect of x on y, and the other is the deviation caused by my model, the noise introduced by my model, my regression sum of squares. So if I look at it this way, at this point there's a total variance, okay? That's the total variance from the mean of that point. Some of it is explained by my model, which is great. My model is great. It's giving me a huge explanation of why this point is up here and not down there. But there's also an additional component, which is, well, this point doesn't exactly fit my model. I have a residual. Okay, so these are all the variances happening in my data. So when I think about how well my regression explains the data, I can think about those sums of squares, okay, divided by the total sum of squares. And this gives me an indication of the explained variance, of how well I'm explaining my variance, and it's called R squared, okay? It is, in a linear model, it is actually that Pearson's R we've seen before, and it's just squared when we think about it, but it's called R squared. It's usually written in a capital R. It ranges between 0 and 1. Remember, the Pearson's R can go from -1 to 1, so this one can go from 0 to 1 because it's squared, right? So we lost all the negatives. So 0 means very poor fit, 1 means perfect fit. There is no deviation, so my regression sum of squares is matching the total sum of square, okay? So I have my explained variances are the same, and my residuals are 0. So when we go back to that example from before with the line and the two models, AA as a function of BB, CC as a function of BB, and we saw that one has a good fit and the other less, then I can look at the R squared here, and yes, it's actually not 0.93, very close to 1, very close to a perfect match. But this model, not so much, okay? I mean, like, what it tells me is if I wanted to know what's happening at this point, I'm actually not that sure. Okay, I'm going to put the dot here, but could have been up here, it could have been down there. It's very hard for me to tell. So what it is the correlation squared, the R squared, or what we called the explained variance. Okay, so the higher it is, the more of that variance is explained by our model. The lower it is, the more of the variance is explained by this stuff, the residual. Okay? Let's see. So I can test a few things in my regression, and a few hypotheses are tested in a regression model. One is that this variation that is explained by the model, the one we just talked about, is not due to chance. Okay, so we're calling that the F test. We'll come to this. I want to know that the slope of the regression is actually significantly different from 0. Okay, so I'm taking the beta parameter, or the B, the slope, and I'm running a t-test on it to know if it's different to 0 or not. This tells me if there's a correlation between the variables. And I want to know, I don't really want to know, but sometimes people want to know, and it comes out in the print, but the y-intercept can be significantly different from 0 or not. Okay. I'm going to come back to why we need a test. So this line is running through the mean of x and the mean of y. And then a slope is fit to it to maximize the goodness of fit. Now you remember the mean comes from a population of samples. There's a distribution of possible means. So my possible lines could be crossing here, could be crossing there, could, x has a distribution, y has a distribution with different likelihoods. This is the most likely mean. This is at the peak of the distribution. And but there are other means possible for my population because my sample has limitations, right? So I can have a population of different slopes, okay, which is why I have a statistical capacity to test whether the slope is different to 0 or not. So if I look at this slope, it looks like that, but like there's also with this type of population and its variance, there's also a chance of a slope that is 0. Okay, and I want to know whether it's likely more than 5% of the time, right? So how do I test these things in a regression? Using the linear model again. So this time AA as a function of BB. Okay, so this is testing this model right here. And LM, remember we made a linear model. And if I look at the summary of it, I get this code, this spit out from the machine. There are two coefficients I'm measuring. One is the intercept, the A, and the other is the slope of BB as a function of AA. Okay? There are only two here. It's a simple linear model. These are the coefficients that it came up with. So it means that the plot intercepts the y-axis at 3.70. So when x equals 0, when AA is when BB is 0, then AA is 3.73. However, there's a standard error around that. Remember we said this is just part of the population. The population has a standard deviation. So there's a standard error to that. I can test that. I have a mean and a standard deviation. I can test that with a t-test. I have a t-value, and I can see whether this is different to 0. And the probability of this being, of me claiming this value is different to 0 and being wrong in my claim is 0.00246. Okay, so it's tiny, 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 much smaller than 0.05. I can significantly say the intercept is different to 0. But what I'm more interested in is this slope. So the slope of, so AA depends on BB in this manner, in a positive way, and every change in BB results in a 0.8 change in AA. That's what this slope coefficient is telling me. Again, there's an error around that. What I really want to know is AA really dependent on BB, or is it just kind of by chance? If they're not dependent, the slope would be 0. BB can do one thing, AA can do another thing. The two are not talking to each other. So I want to know if the slope is different to 0, and this is what this is showing me. That AA significantly depends on BB. Okay, because this is tiny, 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 much smaller than 0.05. Now R gives you these cheat sheets. It tells you significant codes, so highly significant. This is the one you want. 0.05 has one asterisk, one star attached to it. The other things we'll talk about are nonlinear relationships, and we'll do that in